Hello everyone and welcome to our third video in this video series on LiGuard. LiGuard is a research-purposed GUI-powered Python-based framework that allows easy development of dynamic point cloud and image data processing pipelines. In our last two videos, the first video demonstrated the basics of LiGuard and implemented a very basic pipeline of reading and visualizing point cloud data. In the second video, we implemented a complex pipeline. However, that pipeline used only the algorithms and functions that are already available in the algorithmic library of the LiGuard. However, to develop custom pipelines or testing your algorithms, you need to embed that algorithm as a pipeline function of the LiGuard. So this video is about that and explaining how to add a new custom algorithm and embedding it into the pipeline. This also showcases some of the capabilities of the LiGuard, such as doing a lot of basic operations for you. So like embedding a new function into the pipeline is rather easy, and how dynamically you can enable or disable different algorithms without affecting the pipeline execution. So let's jump right into it. The pipeline title is running a deep object detector on moving platform point cloud data, and as the name suggests, it's a pipeline that reads a data that is recorded from a perspective of the moving LiDAR, so from a vehicular point of view. And then what we do is we apply or pass that point cloud data through a deep object detector. Deep object detectors are essentially deep neural networks that are specialized for detecting objects. In this case, the deep object detector is a 3D object detector and it's called Pointpillar. The citation for that is available here, and we are using its implementation of the PyTorch that is available in the GitHub repository here. So we will be applying that point pillar on the data, and then we will be visualizing the results and visually comparing them against the ground truth data that we have. The dataset that is used in this pipeline is a very small subset of the KITTI dataset, and we have in fact used it in our first video of this video series. It has 10 frames and contains point cloud, image, calibration, and ground truth label data. And we do not need to actually implement this stage of the pipeline, as LiGuard has a built-in support for multiple publicly available LiDAR datasets. So we can just use the default reader of the LiGuard, and we do not need to implement a custom data reader for this. Similarly, for the visualization, LiGuard has built-in support for drawing bounding boxes via a very easy to use pipeline. So just passing the bounding boxes in the form of their centers, their orientations, and their extents, LiGuard automatically draws them in the background and also apply the transformations needed for projection of those bounding boxes to the image data. So for example, in the KITTI dataset, the input labels are in camera frame of reference, so it has in the background the transformations to convert those to the LiDAR, the point cloud space. And also if you draw something in the point cloud space, or the frame of reference of the LiDAR, if you draw a bounding box there, it is also automatically projected to the camera space. So the first and the last stage are already complete. The custom implementation that we will be doing is application of Pointpillars on the point cloud data, and then passing the predictions to our visualization pipeline. So the model that we are using is called Pointpillars, and this is its citation. We will be using a PyTorch implementation of it, which is available at this GitHub link. So let's directly dive into developing it. So I'll delete the last one that I created just so we can create everything from the scratch. Fire up the LiGuard. Sorry, I think I am in a different directory. Just open a new terminal in here and start LiGuard. Create a new configuration, and the data source is pretty much standard now. We have explained all of these different paths. So I will just quickly be adding the path to our data. The root path is examples data KITTI. The LiDAR is under Velodyne, image underscore 2, label underscore 2. So all of these different paths are, you can see them here in our examples. Under examples, under data, under KITTI, you will see the data set and the. So this is the path example data KITTI, and then these are the subdirectories that we are adding here. We will enable all of the readings of the camera and the labels and the calibrations. If you hit apply, you can see if the data is loading fine, so you can navigate by pressing the arrow keys on your keyboard. Once you are sure, you can save this pipeline. Let's call it pipeline Pointpillars on KITTI. Okay, and save it. If you see under the processes, the proc category here, these are all the configuration for the algorithms available. So under LiDAR, crop is available, and all these other algorithms are available, but the algorithm that we need is a custom implementation, so it is not available in the standard algorithmic library. So we cannot actually use like these functions or edit them to support this custom function. In order to develop the custom function, we can first close the LiGuard and open our configuration that we just created. So here, the first thing that we will need is to add an entry of this algorithm in our configuration YAML file. This configuration the entry that we will add here will show in the configuration GUI, and this configuration will also be shared across all the processes or all the functions that are available in the LiGuard to all the pipeline processes. So I have actually created a small entry for this algorithm here, so I will just add it here. Okay, let me explain what this is. So this is the name of the algorithm. So LiGuard will be looking for this function under the algo lidar.py. So in the lidar.py, it will be looking for this function. And why is that? Because this point pillar is under proc lidar. So any process or algorithm that you place under lidar category will be looked in this lidar.py. Similarly, if you go for let's say the Caleb here, so it will look under the Caleb.py. Okay, so this is like a standard way of how the LiGuard knows that which function to call and from where that function is located. So in our case, this function must be located under the lidar.py. So let's define this. Now this data dictionary and the configuration dictionary are automatically passed to this function. So whenever this function will be called, all the data that is available in the pipeline and the configurations are passed to this function, so we can use them to implement our function. However, implementing this function will take a lot of time. So what I will be doing is I will copy a function from my I have already defined here. So I will just paste that. Okay, what this function does at a high level is that first of all it gets the logger. So logger is if you want to log any errors or stuff. It checks if the point cloud numpy is in the data dictionary. If it's not, it logs it and then it returns. It also checks this key. So let me explain the other variables that are here. Enabled is a key that must be present under all the algorithms that you all the algorithm entries that you enter or like put in the configuration YML file, because this tells the LiGuard if the algorithm is pre-enabled or pre-disabled, and also allows you to disable the algorithm or enable it during the execution of the pipeline. So this is a standard like variable. The second variable is not necessary, it's an optional variable, but it's also a standard variable. So this activate on key set will look if this point cloud is available. So current point, so there are actually 4 different types of data that are passing through the pipeline. So one is called current point cloud numpy, which has the current point cloud that has just been read into the point cloud pipeline. Similarly, current image numpy holds the data for image, current calib data holds data for calibration data, and current label list has the label list of the current loaded label list. Alright, so the priority we are setting it to 7. Priority is also a standard necessary variable that you have to put under every algorithmic entry here in the configuration YAML. So priority we are setting it to high so that it is called on the last. These 2 variables, however, we have defined because we are implementing this Pointpillars PyTorch implementation by Zulf 0804. This library uses PyTorch to implement the this actually like implementation of the Pointpillars uses PyTorch. And since we are using this repository, I am just adding the path to this repository so that we can import the functions from it. And the path is algo nn Pointpillars. If you go here, you will see that this nn folder is actually not present in your case. So you just have to create a new folder nn and inside it put Pointpillars. And complete all the requirements of the Pointpillars that are given on their the official page of this implementation. So you will need actually some compilations of CUDA code, and also so this is I think the only requirement. Once you have that, other than that you have the requirements of PyTorch and those libraries. That is not the scope of this video because different algorithms may have different requirements. So any algorithm that you want to use, you have to make sure that you have all the requirements filled for it. So we have cloned this repository here and we have already compiled its code. This is another variable that I have added. So this is like a custom tunable parameter. So this threshold, we can increase it to only get very high confidence bounding boxes, or lower it to get even the hallucinated bounding boxes. This is actually a threshold on the confidence score of the predictions. And if you look here in the implementation, how we did it is that, okay, after getting the logger and checking if the data is available and checking if this activation key is set. Okay, so I haven't talked about this one. So this is an optional key, but it is if you use it, then whenever this will this key will be available in the data dictionary, if that algorithm is enabled, it will be called. Okay, otherwise it won't be called. So this is kind of gives you an even more deeper control on when an algorithm, an algorithmic step or a stage of the pipeline, should be called or should not be called. Other than that, it has some keys here. If the point pillar model is not loaded already, we will use it. We'll use some customizations here, all of them to load our model, and define some variables that will be shared in the consequent steps If the we are checking if the CUDA is available, we will be processing it on GPU. Otherwise, we will be processing it on the CPU. We will put the model to evaluation mode because we're just running the inference. And here, if you see, we are converting the current point cloud numpy, which is in the pipeline. So data dictionary shares all the data that is in the pipeline. So current point cloud numpy means the current point cloud data that is available in the pipeline. So we will just convert that to a torch tensor. We will convert if the GPU is available to a CUDA tensor, and then what we will do is that we will pass that data to the model that we loaded, okay, and we'll get this result. Now if you see, the LiDAR boxes are so this like implementation outputs a dictionary of results. So the result LiDAR B boxes is the key for getting the B boxes, and the labels and the scores are defined like this. We will check for all the labels that are there. If the score is, this is here we are testing if it's more than the threshold or less than the threshold. If the score is less than the threshold, then we will just continue. The LiDAR B box we will get to a different variable, and then what we will do is we will get the three different things, which are the center of the LiDAR and the extent of it and the Euler angle of the LiDAR. So in this case, the point pillar only predicts the rotation around z-axis. So we set the x and y axis 0. Z-axis is the upward axis in the KITTI dataset, so we will be just using the orientation around that z-axis here. Similarly, the object classes, the labels that are out, they are numeric values, so we will just be using the we will convert the IDs to the keys here, and we'll get the object classes. The main thing that we are doing to put the predictions back to the pipeline is that we need to create the LiDAR bounding box. And the LiDAR bounding box is actually, so these are just the colors of it based on the object class, and this is the label that we will be passing back to the pipeline. So label in LiGARD is a dictionary, and inside that it has the class, the LiDAR B box and the camera B box. The LiDAR B box and the camera B box actually have same parameters, other than the only difference is that the color of them will be different. If you want a different color, if you want the same colors, the only difference will be because the LiDAR B box color is from 0 to 1, so 0 is black and 1 is white, but for the color for the camera it's from 0 to 255, so you will have to take care of the right color here. Also, there is a key for predicted, so if anything is predicted, it is more highlighted in the visualizer. So if you set the predicted to true, it will help the visualizer to, or you later, to kind of see which of these are predictions and which of these are truth bounding boxes. Once you have this label, you check if the current label list is available, if there is any ground truths available or not. If the ground truths are available, you just append your label to that list, because they all will have a predicted is equal to false. So LiGARD by default knows which of these are predicted ones and which of these are not predicted ones. But if the current label list is not present, and you have to just create a new label list, so so this is just creating that label list and adding the label to that. So yeah, this way we have added an external algorithm to the pipeline of the LiGARD. And if you just remove a lot of, so in this case I have added a lot of checking and debugging code, but if you just remove that, the actual implementation will be actually very short. So if you see, this is a 50 lines code or so to implement from here to mostly here, to implement a neural network algorithm and directly embedded into the pipeline. Okay, so once we have that, let's go ahead and try this. Again, run the LiGARD and open the configuration that we have defined earlier. So if you see now, you will look, if you look here, it should have a you know, the newly added algorithm. So or didn't I save it? I think I forgot to save. So let's like open it up again. All right, pipeline here, yes. So you can see now the point pillar detection is available, and all the variables that we defined there are also shown here. So since all the other things are here, let's go ahead and try to do like a detection here. So in the ground truths, you can see only label is this one person, because the image data only shows that, right? But if you look at this point cloud, actually, you know, when they were capturing this data, there were so many other people that were out of the bound for the camera, so they didn't label those, but they are here. So let's try and see if the newly added algorithm can do that. So we will enable it and we will click apply. So in the background, it is loading the model. For the first time, it takes a little bit more time, but once you have it, it starts detecting. So you see now there are multiple detections. For this pedestrian, it is also detected. And we can like test it dynamically by changing the parameters. So let's set the threshold to like a smaller threshold so that, you know, we get more detections. So probably, oh sorry, we are setting the wrong threshold here. So the threshold here is this one, 0.2. Let's do that and check. Now you can see it has started detecting all these other things, and if you look closely here, the ground truth and the predictions are both there. So the ground truth is now lightly colored and the predictions are more brightly colored. So you can kind of see that, okay, how accurate the prediction is, and with more time we will be adding more algorithms to it to like kind of visualize the intersections of these. And since this is now a part of the pipeline, you can still do all the other things that you previously had. So for example, if you want to just crop the data, okay, you can still do that. It will crop the data. So this data is actually I think already in the crops, but let's say do this, and although it has provided detections, you know, like hallucinated or like the empty bounding boxes, you can use the other like pre-built functions, such as for labels you can remove out of bound labels or remove empty labels. So if any box has, let's say, less than 2 points, just you know, erase that, and you can see like you have that model already now working as a part of this pipeline. So let us actually do something where, you know, the detection is a little bit more clear. So for example, here darker bounding box is the ground truth and this lighter brighter bounding box is the prediction. So you can see that the prediction is not highly, it's not accurately predicting the exact bounding box, but it still is a very good prediction. So the main point that I want to demonstrate here is that, you know, these bounding boxes were predicted in the frame of reference of the LiDAR. However, they are now projected into the images as well. All right, thank you so much, and we will see you in our next video.